Welcome to AI Paper Slot. Today we are jumping right into self-improvements in modern agentic systems, a survey by Ziren and colleagues, published in 2026.
Yeah, this is a really crucial paper for anyone in the ML space right now.
Definitely. So here is your quick course summary to get you grounded. The paper basically formalizes how modern AI agents evolve autonomously.
Right, it takes a super fragmented field and gives it a unified mathematical framework.
Exactly. And they divide self-improvement into two distinct pathways. Pathway 1 is foundation model improvement. So this is the slow, stable consolidation where the system updates its actual neural parameters, its theta.
Using its own self-generated learning signals, which is the key part.
Right. And then pathway 2 is scaffolding improvement. These are non-parametric updates to the agent's operational framework, its sigma. So that covers prompt optimization, memory evolution, and tool governance.
And that one is a much faster loop. Highly iterative and, easily reversible.
Right. So why is this survey mandatory reading for ML engineers and researchers today?
Well, it highlights this massive paradigm shift. We are, moving away from static, frozen models.
Yeah, the era of train it once and deploy it is kind of ending.
Exactly. We're entering an era of dynamic systems that autonomously inspect and rewrite their own operational logic. This is basically the practical realization of the Gödel machine, which is a theoretical concept from decades ago.
Right, but historically that was practically impossible, right?
It was a computational nightmare. You had an algorithm trying to rewrite its own raw assembly code or its own synaptic weights. But today, these modern systems are using natural language as the substrate for self-improvement.
Okay, let's back up a second and unpack the anatomy of these systems. Because to understand how they improve, we have to define what an agent actually is in this framework.
Yeah.
The authors define it as a coupled configuration. So you have the foundation model on one side and you have the operational scaffold on the other.
Right, the core and the framework around it.
Yeah. Before we get into the heavy math of how they interact, I was thinking about this analogy. Is it accurate to visualize the foundation model as the engine of a vehicle? Like the raw underlying compute and reasoning power?
I like that. Yeah, the engine block.
Right, and then the scaffolding acts as the steering and the chassis. The context, the memory, the routing.
That is a highly functional way to look at it, yeah.
Yeah.
The engine is your parameter space, and the steering wheel is your operational logic.
Makes sense.
If we look at the historical attempts at self-modification, the field has basically been trying to rebuild the engine while driving down the highway at 80 miles an hour.
Right, which usually ends in a crash.
Exactly. The mathematical roots of error-driven adaptation, they trace back to Gauss's method of least squares in 1805.
Oh, wow, that far back.
Yeah, but the direct AI lineage really accelerates with Jürgen Schmidhuber's work. In 1991, we had fast weight programmers where one neural network learned to generate the weights of another network. And by 2003, Schmidhuber proposed the Gödel machine. That was a system designed to rewrite any part of its own code, assuming it could mathematically prove the rewrite would increase its future utility.
But the bottleneck with those early systems was always the search space.
Massive bottleneck, yes.
Like if an AI is trying to optimize raw assembly code or tweak billions of individual synaptic weights, the number of possible permutations is just paralyzingly huge.
Yeah, and most of those permutations just break the system entirely. It's incredibly brittle.
Right.
So that was the wall the field hit. The search space for raw code or raw weights is just vast. But the breakthrough of the modern era, which this paper centers on, is that foundation models use natural language as a unified semantic medium.
Okay. So language constrains the search space.
Fundamentally, yes. When an agent today fails a task and evaluates its performance, it doesn't output a massive, incomprehensible gradient vector.
Like a giant matrix of floating point numbers.
Exactly. Instead, it outputs a semantic string. Like, I failed to authenticate the API before requesting the data payload.
Okay, yeah. That natural language critique is infinitely easier to parse and iterate on.
Exactly. Language acts as the shared interface for representation, reasoning, and control.
So following that engine analogy, let's look at pathway 1. The paper calls this foundation model improvement. This seems like the slow burn of actually reaching in and updating the engine block, right? The parameters, the theta.
Totally. Updating the actual neural pathway.
And unlike standard supervised fine-tuning where we rely on, armies of human annotators to provide labels, This pathway requires the agent to induce its own learning signals through execution.
Yeah, it has to teach itself. The paper categorizes three main sources for these intrinsic signals. First, you have intrinsic generative demonstrations.
So the agent generating its own synthetic training data.
Exactly. Second is intrinsic evaluative feedback. This is where the agent acts as a meta-judge. It generates multiple outputs, critiques them, and scores them, creating a preference data set.
Almost like self-RLHF.
Exactly like that. And third is extrinsic exploratory experience. This involves the agent operating in grounded environments.
Like navigating a live web browser.
Or a simulated proxy environment, yeah. And learning from the actual interaction trajectories. When these signals are used to update the weights, the capability gains are amortized across tasks.
So you get stable global changes to the foundation model.
Exactly.
But wait, hold on. If the agent is just training on its own generated data, isn't that a massive AI echo chamber?
Oh, absolutely.
Like the survey cites a lot of recent literature warning about this.
Yeah.
Doesn't the model just drive straight into collapse over time if it's eating its own exhaust?
Yes. This is known as the curse of recursion. If you naively feed an agent's outputs directly back into its own weight updates, the distribution shifts rapidly. Errors compound.
It just amplifies its own hallucination.
It does. The model becomes overconfident in its errors and eventually collapses, completely forgetting the original diverse data distribution it was trained on.
So how does the paper address that?
Well, to prevent this, the mathematics of Pathway 1 require a rigorous quality control operator. The authors denote this as phi sub t.
Okay, so phi sub t is essentially the filter standing between the agent's scratch pad and its permanent neural pathways.
A filter, yes,
Yeah.
but computationally much more active. Before any generated dataset, d sub t becomes a learning signal for backpropagation, it must pass through phi sub t.
What does that look like mechanically?
Mechanistically, this operator might be a deterministic compiler verifying that the generated code actually executes and passes unit tests, or it might be a formal rule-based safety checker, or even a heavily calibrated separate reward model.
Okay, so it mathematically alters the gradients by weighting high-quality synthetic samples and completely dropping the flawed ones.
Exactly. Without a sound phi sub t operator, self-improvement at the parameter level is impossible over long horizons. You just amplify noise.
Right. And because updating those weights is computationally expensive and carries that massive risk of distribution shift, the paper presents scaffolding improvement as the dominant faster loop.
The sigma updates. Pathway 2?
Exactly. We aren't rebuilding the engine, we are dynamically swapping out the steering wheel.
And Pathway 2 requires 0 parameter updates. The weights are completely frozen. Instead, it relies entirely on in-context learning.
Which, for the engineers listening, the paper emphasizes that in-context learning acts as a highly efficient form of meta-learning.
Under the hood, this adaptation is mediated by the attention mechanism's key-value cache, the KV cache.
Let's break down that mechanism, because how does tweaking the scaffold actually change the model's behavior so fundamentally if the engine itself isn't changing?
Well, in a transformer model, the attention mechanism uses keys and values to hold the transient state of the sequence it's processing. The KV cache effectively acts as a short-term associative memory.
Okay.
By optimizing the prompts, the memory injections, or the tool use instructions in the scaffold, you are strategically modulating what gets loaded into that KV cache.
Oh, I see. So you are generating context-dependent weight changes dynamically during inference, without permanently altering a single parameter in the foundation model.
Spot on.
That brings up the evolution of prompt optimization, which the survey tracks beautifully. Like, we used to just do simple scalar feedback optimization, right?
Right, running a prompt, getting a numerical score, and tweaking it.
Yeah. Then we moved to qualitative feedback refinement using language critiques. But the current frontier mentioned in the paper is textual gradient optimization. What exactly is a textual gradient?
Think about traditional deep learning. You use backpropagation to calculate a numerical gradient.
Right, and that gradient tells you the exact direction and magnitude you need to adjust a specific weight to minimize your loss function.
Exactly. Textual gradients apply that exact calculus concept to natural language. Instead of a vector of floats, you use the foundation model to generate a semantic critique.
Could you give an example?
Sure. Say a prompt fails to extract the right data. The textual gradient might literally be the sentence. The instruction is too vague about the JSON schema format. Specify that nested arrays are required.
So the critique itself acts as the gradient vector.
Yes. It tells the optimizer, which is usually just another LLM called the semantic direction and magnitude of the error, The optimizer then applies this textual gradient to update the prompt.
That is wild. It is backpropagation where the substrate is vocabulary rather than floating point numbers.
It's brilliant, honestly.
And this scaffolding evolution isn't just about prompts. It applies heavily to tool governance too, right?
Oh, massively. Agents are no longer just handed a static list of 10 APIs.
Yeah, the survey outlines dynamic tool routing, where the agent decides which tool to use on the fly based on the context.
And iterative refinement, where the agent learns how to format its tool calls better after getting syntax errors.
But the most advanced stage they mention is autonomous tool creation. Like, the agent actually writes its own Python scripts to handle missing functionalities, executes them, and adds them to its own toolbox for future use.
It's reshaping its own action space dynamically. So the agent hits a wall, realizes it lacks the function to parse a specific proprietary file format, writes the function, tests it, and then commits that tool to the scaffold.
It's basically a self-organizing toolbox.
Exactly.
But if Pathway 2 is all about these fast, reversible adaptations, wiping the scratch pad when a textual gradient fails or a new tool breaks, how does the agent actually learn anything permanently without touching the engine? It has to store those hard-won lessons somewhere, right?
Right, and that naturally bridges us to memory governance. The survey actually elevates memory from a passive storage drive to a self-governing engine.
Which they argue is arguably the most complex component of the scaffold to engineer correctly.
It is incredibly difficult to get right.
So the paper breaks memory down into 4 distinct objects and maps out the critical failure modes for each. To make this concrete for you listening, let's imagine an agent tasked with building and maintaining a complex web scraper over the course of a month.
Okay, good scenario.
It has to navigate logins, changing DOM structures, rate limits.
A perfect scenario to illustrate the memory objects. So the first object the paper identifies is process trails.
What are those exactly?
These are distilled lessons, routines, or semantic summaries of past interactions. In our web scraper scenario, after spending an hour figuring out a complex OAuth login, the agent might save a process trail that basically says, to log into this domain, always request the secondary auth token first.
Right, that makes sense. That's great for persistence and saves a ton of compute next time.
It does. But the paper identifies the failure mode here as summary bias.
Which is what, like playing an internal game of telephone?
That's exactly it. Summary bias occurs when the agent continuously compresses its own past routines. The agent abstracts the scraping logic to just use the auth token, but in the compression process, it throws away the nuance that the token requires a specific user-agent header.
Oh, I see. So over time, these distilled heuristics become stale or overly rigid, and the agent fails because it compressed away the vital context.
Right, which logically leads engineers to rely on the second memory object, curated raw content.
So instead of summarizing, you just save the exact artifacts. The raw code snippets, the exact HTML payloads, the full error logs, high fidelity, zero loss of nuance.
Yes. But then you hit the opposite failure mode, which is context bloat.
Because it's saving everything.
Right. If the agent saves every raw HTML payload it encounters while scraping, the retrieval system pulls all that junk into the active context window later.
And the signal-to-noise ratio just plummets.
Inference costs skyrocket, and the foundation model loses the ability to reason because it's essentially drowning in raw logs.
Okay, so that's a dead end too. What's the third object?
Object 3 is integrated external knowledge. This is shared factual state.
So the agent grounds itself in an external database, like an updated documentation repository for the website's API.
Exactly. It is highly verifiable. But the risk there is staleness.
Right. If the target website updates its API endpoints and the external knowledge base isn't synchronized, the agent's memory becomes structurally inconsistent with reality.
And it will confidently execute actions that are guaranteed to fail.
Wow. Okay, and finally the fourth object.
Latent embeddings. This relies on vector spaces for fast, compact, associative carryover. The agent embeds its past successful scraping, runs into high-dimensional vectors, and retrieves them via similarity search.
Okay, that sounds robust. What goes wrong there?
The failure mode here is probably the most insidious representation drift. Because the memory is implicit, it's just a dense vector of numbers, it is incredibly hard for an engineer to debug.
Oh, I see.
As the agent encounters new domains, the vector space shifts. A query that used to retrieve the login logic might silently start retrieving completely irrelevant formatting code.
It's just silent corruption. You wouldn't even know it's happening until it breaks.
Exactly. So to manage these 4 objects and their failure modes, the survey formalizes a continuous CRUD cycle for agents. Create, read, update, and delete.
And they stress that while creating memory must be selective, deletion is the actual bottleneck.
Deletion is so hard. If an engineer sets the pruning policy too aggressively, the agent develops amnesia and forgets the OAuth logic entirely.
But if the pruning policy is too loose, you flood the KB cache with outdated noise.
The deletion policy is really what separates a toy agent from an enterprise-grade system. An agent must be able to autonomously recognize when a piece of knowledge is no longer utility maximizing and just purge it.
It's a massive engineering challenge. So with the agent constantly churning through this CRUD cycle, generating textual gradients, writing new tools, and occasionally updating its fundamental weights, how do we actually evaluate progress?
Yeah, that is the million-dollar question.
If I'm an ML researcher, how do I know the agent is becoming fundamentally more capable rather than just overfitting its scaffold to basically hack a specific benchmark?
Evaluation is perhaps the most urgent bottleneck discussed in the survey. If you give an agent unbounded iterations and a really fast scaffold, it will eventually brute force its way to a high score on almost any static benchmark.
So the benchmark scores are effectively meaningless if you don't control for iterations.
Right. The paper argues we must move away from measuring peak scores and start evaluating the full performance trajectory across time.
So we have to track regression rates on previously solved tasks, too.
Exactly. Because of the dynamic nature of the scaffold, an agent can induce goal drift.
Right. It might spend a week optimizing its tools to become, say, 20% better at parsing dynamic JavaScript. But in the process, its memory dilution policy accidentally purges how to handle basic static HTML.
Yes. You also have to continuously track safety policy violations across these self-modification iterations.
Which brings up a massive structural asymmetry in deployment that they talk about. Scaffold updates, like tweaking prompts, updating the vector database, adding a tool, those are fast and easily reversible.
But relying purely on the scaffold is expensive at inference time because your context window is always basically maxed out.
Right. So eventually, to lower compute costs, you want to bake those hard-won scaffold lessons directly into the model's weights. You want to move from pathway 2 back to pathway 1.
The authors call this parametric consolidation.
But they label parametric consolidation as a lossy compression. Why lossy?
It is a really profound insight into how these systems actually learn. Imagine an agent navigating a complex coding task. It makes a mistake, reads the compiler error, queries its memory, generates a textual gradient, adjusts its prompt, and finally produces the correct code.
Okay.
That entire trajectory is a rich metacognitive process. When you use that final success to fine-tune the model's weights, standard supervised fine-tuning basically just minimizes cross-entropy on the final output.
Oh, wow. So it distills the success, but it inherently biases the model toward average case execution. It's like a student studying for an advanced calculus exam by just memorizing the final correct answers printed in the back of the textbook.
Yes, perfect analogy.
They throw away all the complex, messy scratch work they use to navigate the tricky edge cases. During the test, they look like they know the math perfectly, right up until a slightly different edge case pops up.
And because they lost the metacognitive process of how to recover from an error, they just fail completely.
That is wild. That captures the structural danger perfectly. Parametric consolidation basically discards the rare but crucial error recovery strategies that the agent discovered during exploration.
The neural weights learn the happy path, but they lose the dynamic scaffolding that allowed the agent to survive when things went wrong in the first place.
So looking forward, how does the field actually solve this asymmetry? The paper points heavily toward test-time continual adaptation as a major future direction.
Yeah, test-time continual adaptation is the attempt to bridge the gap. Instead of massive batch updates to the frozen parameters, you allow the model to dynamically update its retrieval mechanisms and routing weights on the fly during deployment.
So it gives you the real-time adaptation of the fast scaffold loop, but with better compute efficiency.
Exactly. And without eroding the long-term global performance of the core model, it prevents catastrophic forgetting while allowing the system to handle distribution shifts in the wild.
Which leaves us with a rather chilling paradoxical thought raised by this framework.
The safety paradox.
Yeah. Think about the safety implications of that lossy compression we just talked about. If distilling behaviors into weights mathematically discards those messy edge case recovery strategies, then technically any update to the foundation model's weights invalidates all prior safety bounds.
It is terrifying, mathematically speaking. Every single time the model self-improves its parameters, it might be unlearning the exact cognitive nuances that kept it aligned in edge cases.
It is the defining safety paradox of continuous adaptation. If the weights are shifting, your previous safety guarantees are mathematically void.
Right. So how can the industry ever deploy truly continuous, self-improving agents in the wild if every single parameter update requires a full, from-scratch adversarial testing suite just to ensure the guardrails haven't been compressed away?
It is a massive problem the field has to solve before these systems are granted open-ended autonomy.
An incredibly complex engineering hurdle, yeah.
Something to keep in mind as these architectures scale. That wraps up our analysis for today. We highly encourage all of you building in this space to read the full survey, Self-Improvements in Modern Agentic Systems, to dig into the formal mathematics behind these pathways. Thanks for joining us on AI Paper Slop.